Welcome to a lesson in hypothesis testing for independence and homogeneity. So a little bit about where we're going. Previously, we were talking about a goodness of fit test, and we focused on analysis of categorical data that could be separated into different categories, which are often called cells. And the hypothesis test that you're using here is that the observed counts agree with some claimed distribution. Actually, we will do a quick review of that before moving on to contingency tables. And the contingency table is a two-way frequency table which has two or more rows and columns. There are really two types of hypothesis testing that we can do with contingency tables that we will be exploring. One of them is the hypothesis test of independence, where you're determining that the row and column variables are either independent or dependent. And the other type of hypothesis test is homogeneity, where we're looking and seeing whether the distributions of two populations are the same, or if they're not. Both the goodness of fit test and the contingency tables use a chi-square distribution, not to be confused with the chi-t in a square. So what we're going to do first is going to be 3 videos in this series. The first video series will be about the goodness of fit test, and as a review. The other 2 videos will have to do with the contingency tables, and we will actually look at independence as one video and homogeneity in the other video. So let's get started. So to review the idea of the goodness of fit test, we're going to do a fun example involving M&Ms. And so the hypothesis test of a goodness of fit test is that the observed counts agree with some claimed distribution. Now these claimed distributions might be equal proportions or equal frequencies, or they may be unequal, like unequal proportions or unequal frequencies. And we usually know that ahead of time before we begin running the hypothesis test. In order to do this, the data can be entered in one column, and the different categories are going to be the individual rows. And when I be entering, like in any statistics software, the type of software we're going to be using for this example is Minitab Express. And again, as I had said earlier, we're going to do an example with M&Ms. So this is actually taken from a blog. One of the authors who works at a statistics company was doing their company collects M&Ms as part of what they do. So the author of this study involving M&M's candies collected a sample using good sampling methods consisting of 108 red candies, 133 orange candies, 103 yellow candies, 139 green candies, 133 blue candies, and 96 brown candies. And what we want to do first, a reasonable claim would be is that M&Ms are produced in equal proportions, meaning that you will have the same amount of each type of candy. So let's test the claim that M&M candies come from factories where the candy's color is produced in equal proportions at the 0.05 significance level. So again, we're going to go back to those ideas of the individual components of a hypothesis test. We'll identify the null hypothesis and the alternate hypothesis from beginning claim and express both in symbolic form. Again, you want to, as we've done before, to identify the claim and counterclaim. Then we want to identify the critical values. And in this case, because it's a non-normal distribution, we want to identify the critical values for the specific chi-square and degree of freedom being used. And you want to sketch a graph, or have a software that does sketch the graph for you. Again, this is a critical point, being able to do this because your further analysis is determining whether you're in the region of rejection or not. You can't tell that without a graph. Then what we'll do is calculate the value of the test statistics given the claim and sample data. We'll identify the p-value, and then lastly, we state the conclusion regarding the null hypothesis in the context of the problem. So again, this is what we're going to be doing. We're going to be testing the claim that M&M candies come from factories where the candy's color is produced in equal proportions at the 0.05 significance level. So let's first of all open up Minitab. This is already opened up, and you'll notice that over here I've already entered in the data from the information given in the problem. So in column 1, gives the candies colors. In column 2, we have the count of M&Ms for each of these. Okay. Well, first of all, let's take a look. And so these are already entered in. Let's go now through and let's start looking at what we have for our claim or counterclaim and our null hypothesis and alternate hypothesis. So we're using a goodness of fit test to test the hypotheses that the observed frequency distribution fits or conforms to some claim distribution. We're making the claim that is coming from factories where the candy's colors produced in equal portions. So that would imply that you are expecting the same frequencies for each of the candies that are produced. And so the claim is that the candy's color is produced in equal proportions. The counterclaim is that the candy's color is not produced in equal proportions. So our null hypothesis is that the frequency counts agree with some claim distribution, and that the alternate hypothesis is that the frequency counts do not agree with the claim distribution that we have here. So we're going to investigate using Minitab Express. So we've now stated our claim or counterclaim or null hypothesis and alternate hypothesis. From that, we're now going to go and make a sketch of the graph. We'll use a software to assist with this as well. Okay, the data is already entered. To create a sketch of a graph, what we want to do is go to the probability menu. We would want to go to the distribution plot, and we would want to display the probability. And what we're going to do next is it always will default to the normal distribution. In our particular one, we want to look at the chi-square distribution, so that's where we're going to go to. It's going to ask the number of degrees of freedom. Because there are 6 categories, we will use one less. Degrees of freedom is always one less than the number of categories when we're looking at a goodness of fit test. So what we're going to be doing is it's going to be 5 degrees of freedom. Our significance level was 0.05, so let's now see what that looks like. So here's our distribution plot, and that's our chi-square distribution plot. We also get the critical value, which separates the region of rejection from the region of non-rejection, to be chi-squared is equal to 11.07 approximately. And here our region of rejection here is 0.05. So what we're going to then do is run some of the statistical tests to determine what's actually going to happen. To do this, so we're going to make sure we'll make a note of this and take a screenshot of that, and that will be part of our final output when we're starting to make analysis. And really what we want to find out is when we run the test statistic, is it going to be in here, which is the region of non-rejection, or is it going to be over here, which is the region of rejection? Okay. So in order to run the chi-square test, we would go to tables, and I use a Mac, so your menus might be a little bit different if you use a PC. So in here what we're going to be doing is we're going to be choosing the chi-squared goodness of fit test. And then let's take a look. Also, we have, okay, our categorical data is actually summarized, so we'll switch that over. Summarize data in a column. And then it's asking for observed counts and also the category names. So let's see, our observed count comes from column 2. Our category names, it says it's optional, but we did write our category names when we typed in the data. So that's it contained in C1. And you can actually do a couple of different tests. We are going to be doing the test of equal proportions. There's also be a case where it's specified proportions or proportions based on historical counts. For the one that we are testing the claim of the equal proportions. When we look at display, there's nothing that we need to do to modify this. This is fine as it is. Okay, let's do it and see what we get. So a couple of things that occur is you'll notice that it does observed and also expected counts. Our expected counts based on taking the sum of the observed and dividing it by the number of categories. So we would be taking the summation of 108 plus 133 plus 103 plus 139 plus 133 plus 96. Add those numbers all together, and then you would take that and divide it by the number 6, since there are 6 categories. When we do equal proportions, that's how it's calculated. That's where the 118.667 comes from. Okay, so a couple of things to note. We also have the results of our chi-square test, which we're going to look at a little bit more analytically later. Our test statistic of the chi-squared is going to be 14.30, and our p-value is going to be 0.0138. And that's something that we're going to record and use. Also over here you'll see that the individual cell's contribution to the chi-squared, and what it is this test statistic that you see here is the result of adding each one of these individual chi-squared, adding them together, and that is where the 14.30 comes from. So we're going to switch back to the PowerPoint presentation and do a little bit of further analysis now. Okay, so just to do a quick summarization. Our critical value is 11.07, and that's based on the graph that we had originally created. When we run the test, degrees of freedom are 5. The chi-test statistic is 14.30, and our p-value is 0.01, approximately. Okay, so that would tell us that our test statistic is right about there. It is in the region of rejection. And we also notice, because 14.3 is greater than 11.07, so our guesstimate is going to be around here where you see this blue arrow. Furthermore, our p-value is also smaller than the significance level. So this is going to tell us a couple of things. What we're trying to do is make a conclusion. First of all, do we reject or fail to reject the null hypothesis? The null hypothesis being that it's all equal proportions. And then is there sufficient evidence to warrant the rejection? Well, we're going to reject the null hypothesis because there is sufficient evidence to warrant a rejection of the claim that the observed outcomes agree with the expected frequencies. So it does not. We reject the null hypothesis. That would tell us that the M&M candies were not produced in equal proportions, and it's statistically significantly so. So that's pretty interesting. Okay, so the candies are not produced in equal proportions. That we rejected. So the author of this study, who was doing this originally, contacted the parent company of M&Ms, which is the Mars company, and found out that the M&Ms are produced in 2 different factories in the United States, one in Cleveland, Tennessee, and the other one in Hackettstown, New Jersey. And since 2007, both factories produce M&Ms in different proportions. So when you look at the New Jersey factory, which is on the left, you'll notice that the M&Ms are being produced in different proportions than the one which is the Tennessee factory. So one would be curious, is the M&Ms that the author sampled, was it produced in the New Jersey factory, or was it produced in the Tennessee factory, or who knows where else it was produced? So what we're going to do is actually run these 2 tests to see which, it must be one or the other, we think, unless it's a rogue company making M&Ms that nobody knows about. But we can actually use statistics to figure this out. So we're going to do this one at a time. Let's just first of all see if let's test a claim that the M&M candies that the author had sampled came from the New Jersey factory. Again, we'll run it at the 0.05 significance level. So again, our claim is that the candies colors produced in the stated proportions that you see over here. So 25% blue, 25% orange, 12.5% green, yellow, red, and brown. So that's the claim. The counterclaim would be that it's not produced in the stated proportion. So again, the null hypothesis is that the frequency counts agree with the claim distribution, and the alternative hypothesis is that they do not. So let's do some tests. We're going to go over here, back to Minitab. Now notice that when the original graph that we would produce for the chi-square distribution is not going to change, because it's still going to be 5 degrees of freedom. What will change is the statistical test that we run to test whether the distribution that we currently have in the sample conforms to the claim distribution of the New Jersey factory. So this is still the same. Now let's look at the rest. So we're going to go back to Minitab. So I'm going to switch windows. And this was from the last test, but we're going to run it again. And let's see, we're going to go to Tables, chi-squared goodness of fit. And it's going to ask us the same questions. We do still have to change the summarized data in a column. Observed is in column 2. Category names is in column 1. Our test is not now equal proportions, it's going to be specified proportions. And what you end up doing is you end up typing in the proportion for blue, the proportion for brown, the proportion for green, orange, red, and yellow. That's what we're going to do. So we would end up typing it in, so that's what we're going to do next. And let's take a look. So for blue, the stated proportion is 25%, so we're going to change that to a decimal form. That's 0.25. Okay, for orange, it's also 0.25. And for brown, it's 12.5%, which is 0.125. Green is the same, 0.125. Red is the same, 0.125. And yellow is the same, which is 0.125. That should do it. So I did switch it to the test of specified proportions because those are the ones that we're testing it against. All right, click OK and let's see what happens. So as you can see over here, these are the results that we have from the chi-squared goodness of fit test, so for the count of M&Ms, when we do not have the same proportion. So you'll notice that here the tested proportion is given in this column here, which says test proportion. To figure out how these expected values were determined, what you do is you take the sum of the observed frequencies times that given test proportion, and that gives you the expected value, the expected frequency. When we look at this table, first of all, a couple of things will jump out at you. The chi-squared test, you notice the chi-squared is 57.65, and their p-value is so small that it says it's just less than 0.0001. So you'll notice that it's going to, if you know where this is going, we know that we're going to end up rejecting the null hypothesis because our p-value is super, super small. Okay, let's switch back to the PowerPoint presentation. So again, the original value here, this was from the original graph, that isn't going to change. And then again, this is a summary of what we did here where we entered in the proportions. And our chi-square test, this is also summarizing here what we have. So let's see what we can make from it. Over here, this little blue arrow represents where our chi-squared, it's so huge it's off the graph. So we are in the region of rejection, and we're so far to the right of the region of rejection, there's barely any area under the curve to the right of it. Our p-value is super, super small. So that gives us a good conclusion that we're going to reject the null hypothesis that it came in the, again, the null hypothesis is that it is whatever the proportion that was claimed. This sample is not consistent with coming from the New Jersey factory. There's sufficient evidence to warrant a rejection of the claim. The observed outcomes agree with the expected frequencies. The M&Ms do not come from the New Jersey factory. Okay, so what do we do next? We've ruled out that the M&Ms that the author sampled came from the New Jersey factory. We do know there's a second factory, so let's run it. The second factory is in Tennessee. It has a different grouping of stated proportions. The test that we would run is going to be identical, so I'm not going to switch over to Minitab to run it again. I have already run the results through Minitab, so we can summarize some of the things that we find out. Again, we're going to test the claim that the M&M candies come from the Tennessee factory at the 0.05 significance level. Same claim, the candy's color is produced in the stated proportions. The counterclaim is that the candy's color is not produced in the stated proportions. And these are our null and alternate hypothesis. Null is that it agrees with the claim distribution, and that the alternate is the frequency counts do not agree with the claim distribution. So let's see what happens. Originally, our sketch of our graph of what would be the critical region is going to be the same. It is the same candies that we're looking at, in that there are 6 different categories. So that's this degree freedom of 5. Significance level is the same. So critical value of what we're testing against is 11.07. We would end up entering it the same way, unequal proportions or specified proportions, and we would enter in the given proportions specifically. Now, one thing you have to be careful with Minitab is that it will organize alphabetically your category names. Your category names might not be given in alphabetical order, so just always double check what you're typing in, because there's no way to sort it to a specific order. Minitab will always default to putting things in alphabetical order, even if your given category names are not in that order. So always double check what you type in. Okay, so when we run the chi-square test, we end up with a chi-squared value, a test statistic of 6.07, and our p-value is 0.2991. So if you were thinking about where that is located, it approximately is there. So we are not in the region of rejection, unlike in the other two examples where we were. So we would fail to reject the null hypothesis. There is not sufficient evidence to warrant a rejection of the claim that the observed outcomes agree with expected frequencies. So it is possible that the candies did come from the Tennessee factory. So one of the things we can say from this is, okay, it's possible that the candies did come from the Tennessee factory based on the statistical test we ran, which is interesting. So, based on what we know, M&M candies are produced in 2 different factories in the United States. Running the statistical test, we ruled out that it's in the New Jersey factory, and we, based on the statistics, we failed to rule out Tennessee. Now, based on the fact, we could then infer that the candies came from the Tennessee factory, which is kind of interesting. So the epilogue is the goodness of fit test was used to test the hypothesis whether the observed frequency distribution fit conformed to the claimed distribution. The only one that it fit with was the Tennessee factory. It was not equal proportions, and it was not from the New Jersey factory. The data is consistent with candies produced in the Tennessee factory. And that does it. That is your first of 3 videos on this topic. This was a review of goodness of fit. The next video will have to do with contingency tables and looking at that. All right. I hope you found this helpful.